Large neighborhood search is a technique to discover good feasible solutions very quickly to our optimization problem. We can view this technique as a hybridization between CP and local search. So one weakness of constraint programming, even when we have a good heuristic, is that we will dive quickly by using depth-first search. We will dive on the left of the search tree, and we will be stuck in that region of the search tree for a very long time. And when you will stop, for instance, because you have set a timeout to your search, when you will stop the search, you have only explored a tiny fraction of the entire region of the search space. So for instance, you might dive in that region and then you will be stuck, okay, because this other region that is still left unexplored is pretty huge, and you will not have the time to go there given the time limits that you have set for your problem. So the solution to that is to adopt a kind of local search style to be able to discover good feasible solutions faster. When we will get stuck for a while in the search tree, we will take a very radical decision. We will restart from another space, from another region of the search tree, and we will intensify the search where it looks promising. For instance, after a few seconds, you jump from one region to another region, but you stop very quickly so that you have the time to explore different regions. How we proceed is in 3 steps. First, you find a first feasible solution. Depending on the problem, it might be already difficult to find a feasible solution. But if you think about, for instance, a traveling salesman problem and the graph is pretty dense, that's not so much an issue to find a feasible solution. You can even use a grid heuristic, a greedy algorithm to find the first feasible solution. Then you have your feasible solution and you have the search, let's call it S star, that's the best feasible solution. And you will try to explore some modification to that one, and you will explore a neighborhood around that solution. And this neighborhood that you will explore it using constraint programming, using CP. How do we do that? We do that by relaxing some variables of the current best feasible solution. So we take the solution S star and we restore some variables to the domains that they had initially in the model. Okay? And then you will re-optimize, you will refix some of the variables by using CP. And if you are able to improve the current best feasible solution, of course, you replace it and you start from the step 2. And you loop like this again and again until, for instance, you have reached a given number of iterations of large neighborhood search iterations. But it can be more general than that, okay? Sometimes relaxing the problem might, for instance, be to fix some of the precedences between some of the tasks if it is a scaling problem, okay? So it doesn't need to be really fixing the values to the values that they take in the current best feasible solution S star. It's a very generic framework. It really depends on the problem. The advantage of LNS over standard local search is that generally you don't need a meta-heuristic to avoid local optima, because the neighborhoods that you will explore is so large that there are many ways to escape from local optima. So there is no need to use, for instance, taboo search strategies or stuff like that. And the ease implementation is also a very strong asset of this technique. Because when you design a local search approach for a problem, you also need to design the way to explore the neighborhoods. But here we are relying on CP to explore the modifications. So we are relying on the propagation to explore the modification around the current best feasible solution. And the scalability here is also very good. It's the scalability of local search. So we have a very good anytime behavior by using this technique. By anytime behavior, we mean that if you, for instance, would like to allocate a very short amount of time for your optimization, let's say 2 minutes, within the 2 minutes, you will find a very good feasible solutions, very good in terms of objective value, okay? And that's not necessarily the case if you use standard CP and standard depth-first search. Let's study one problem and how to adapt this problem using large neighborhood search. The problem that we will explore is the quadratic assignment problem that we have already seen in the previous lectures. So again, in this problem, you have only one vector of decision variables. Okay, that's also the same for the TSP. For instance, you have an array X of decision variables. And in that problem, you only have the order difference. You have the element constraint to compute the weighted distance between the warehouses and the location where you place these warehouses, and you want to minimize the total objective, that is the total amount of weighted distance in your quadratic assignment problem. That's the standard depth first search model. How to adapt this model to have large neighborhood search, this is what we will see now. You will see that the adaptation that we need to do are very, very small. They are very small and easy to understand. A first thing that we need to add to our model is this. This array will represent the current best feasible solution. We call this vector of integer x best. It will store the current best feasible solution for the decision variable x. So every time there is a new feasible solution, we loop over the n indices and we capture the value of the best solution, and we'll store that in the corresponding x best entry. Okay, so that's really the line that you need to add just to make sure that x best will always maintain the current best feasible solution to your problem. And then here you see that we already have the search there, okay, which is there. And then you will use this search to optimize subject to some constraints. And the constraint that we will add there are the constraints of the relaxation. So we will fix almost all the variables except a tiny fraction of the variables that we will not fix when we will restart the search. So we restart the search. So we optimize subject to the constraint that the variables that will be past this random filter will be fixed to the current best solution that you have, that they have. So x of j is fixed to the x best of j. And the chance that you have to post this constraint is 70% of the chances, because I use a random number generator there. So again, I repeat, so I scan here all the variables. I flip a coin, and with 75% of chance, I will fix the variable xj to the best value in the current best feasible solutions. But all the other variables are free to take the value they want. And this is the mechanism that is used to explore a perturbation, to explore the possibility to improve the current best feasible solution. Okay, so we relax 25% of the variables when at each restart that we have here, and we will execute this loop for a given amount of restart. Okay, for instance here it's for 1000 restarts. There is one additional parameter to the LNS that is very important, is that when you do the optimize subject to, you need to fix a limit so that you do not search for too long with this given relaxation. Okay, and the limit that we'll fix here is exactly 100 backtracks. So the search here, the search that you start, the optimize subject to, has a limit of 100 backtrack. And so that's the predicates that you can give here to your search. And so we will use in the closure here, the statistics of the search. We will get the number of failures. If we realize that the number of failures is larger than the limits that we want to impose of 100 backtrack, then this will have as a consequence that this restart is stopped. And so we will go for the next iteration, and we'll start again with another relaxation of 25% of the variables. So again, the modifications here are very small. You just need to record the current best feasible solution, and then you will do some restart, okay, here. And at each restart, you post that 75% of the variables are fixed to the current best value that they have. Of course, it really depends on your problem. Okay, so the way you should fix these meta parameters, you should play a little bit with this value and experiment with it. Okay, you might also imagine a kind of adaptive scheme. When you get a little bit closer to the optimal objective function, it might be a good idea to relax a little bit more than the limit than only fix it for 100 backtrack. Maybe you will need a little bit more backtrack, and maybe you will need a little bit more than 25% of variables that are relaxed. It really depends on the problem.